teaching stereochemistry. Stereochemistry is nothing but chemistry in 3 dimensions. So let's see what's the definition of stereochemistry. Stereochemistry is a branch of chemistry that deals with 3 dimensional structures of molecules and their physical effect on their physical and chemical properties. So what is the stereochemistry? It's the spatial arrangements of atoms. It's the spatial arrangements of atoms that form the structure of molecules. So how the atoms are attached to to different thing in the space is studied in stereochemistry. It's an important branch of stereochemistry, study of chiral molecules. So chiral molecules are studied on the under the branch. It's a branch in stereochemistry. The stereochemistry is also known as 3D chemistry because of the prefix stereo, which means three-dimensionality. So we study the chiral molecules under the heading of stereochemistry. So where does the stereochemistry plays important role? Stereochemistry plays an important role in biochemicals, medicines, and tools for studying mechanism. Why the medicine? So if you know, the configuration determines how the drug or your target, ligand binds to your target. So if there is a change in configuration, the binding will not be proper. So that plays a very much important. How the enzymes binds to the substrate can be studied having the knowledge about your stereochem, because a known exact configuration of a molecule will be necessary to bind properly to the target. To study different mechanism, it is very much important in studying in the mechanistic approach. So stereoisomer comes from the word isomerism. So what is isomerism? The isomerism is the existence of a molecule that have the same number of kinds of atoms. Means they have got the same molecular formula, but they differ in their physical or chemical properties. So they have the same formula, but they differ in the chemical and physical properties. So let's see the types of isomerism. So there are basically 2 types of isomerism, that is structural isomerism and stereoisomers. The stereoisomers are further classified into optical isomerism and geometric isomerism. Optical isomerism deals with the chiral, whereas geometric isomerism depends upon your double bond and cyclic compound geometry, according to the spatial arrangements across the double bond and the restricted rotation. Now, structural isomerism contains chain isomerism, positional isomerism, functional isomerism, metamerism, and tautomerisms. Okay. So, isomers, as I said, it's a different compound with the same molecular formula. The structural isomers, they differ with each other in their bond with the to which they are atom. So let's take an example of N-butane and isobutane. In N-butane, it's a linear, whereas in case of isobutane, it's an branched chain carbon. Okay, so this is an example for your structural isomerism. Now, stereoisomers are isomers that have same molecular form. You see cis-butane and trans-butane, they got the same molecular formula, but the bonding sequence, how they are bonded in the 3-dimensional structure orientation in the space differ. If you see in case of cis-butane, the 2 groups, methyl groups, are on the same side, whereas in case of trans-butane, the 2 groups are on the opposite side. Okay, this is how they differ in the spatial arrangement. So the difference in spatial arrangement in the space is known as stereoisomers. So definition: stereoisomer, the compound which have same connectivity but different arrangement in the space. So they have got the same arrangement. If you see, okay, if they are the same connectivity, it is connected to same. Your methyls are on the same carbon, but the way they are arranged is different. Some other examples are forms are enantiomers. They are formed non-superimposable mirror, whereas diastereomers that are non-mirror. These are some of the classes of your stereoisomers. Now there are some more definitions that you have to know. Asymmetric center, chiral center, or stereogenic, they are all the same. They are nothing but sp3 hybridized carbon with 4 different groups attached to it. It is an sp3 hybridized carbon atom with 4 different groups attached to it. It has 4 different groups attached. Now what is chiral compound? The definition of chiral is a compound which has ability to rotate the plane polarized light. That means it shows optical activity. It should rotate the plane polarized. A chiral will not rotate the plane polarized light. So that's a chiral one. Optical activity is the ability to rotate the plane polarized light. It is the ability to rotate the plane of plane polarizer. That is known as optical activity. Polarimeter is a device that measures your optical rotation of a content. So you come to know whether it is rotating in the right direction or left direction. The degree of rotation can be measured using polarimeter. So now let's come to the structural or constitutional isomerism. First is chain or skeleton isomer, the same molecular formula but differ in the connectivity of the carbonate. So one is linear and one is branched, that is N-butane and isobutane or cubical. In case of N-butane, it's a straight chain, whereas in case of 2-methylpropane or isobutane, it is a branch. So this is an example of chain or skeletal isomerism. The next comes is your positional or it is also known as regioisomers. What do you mean by this? They have the same molecule but they differ in the position of the functional group on the carbon or any atom. So what happens? Let us take for the example 1-pentanol. It's the OH is on the first position. In case of 2-pentanol, it is at the second position. In case of 3-pentanol, it is at the third. So this is how they differ. The position of the functional group, that is your OH, is different in each and every molecule. So this is an example of positional isomerism or regioisomerism. Other, in case of aromatic compound, it is orthoxylene, metaxylene and paraxylene. If you see, it has got 2 methyl groups substituted in your phenyl ring. So in case of orthoxylene, it is 1,2-dimethylbenzene. In case of meta, it is 1,3-dimethylbenzene, and in case of para, it is 1,4-dimethylbenzene. All the 3 structure, if you see, only thing that differs is the position of your methyl with respect to your another methyl group. Ortho, meta, para. So these are the example of positional isomerism. Next is functional isomerism. So what is functional isomerism? Like case of ethanol and dimethyl ether. Both the compounds have the same molecular formula, that is C2H6O, but they differ. One is your alcohol and one is your ether. Similarly, the example of propanol and propanol. Both the things contain 3 carbon, 1 oxygen and 6 carbon. Okay, hydrogen. But only thing is that propanol is a 6 carbon, so it's an aldehyde, whereas in case of propanol, acetone, it is an ketone. So there is a difference in the functional group. Your molecular formula is same, but the function is the same carbon, C2H6O. They can be there in 4 different forms. One is alcohol, ether, aldehyde, and a ketone. So this is the example of functional ketone. Next is metamerism. So what is this metamerism? If you see the examples of dimethyl ether, methyl propyl ether, and isopropyl methyl ether, see all are ethers, but the functional group is also same, but the alkyl group substitution arrangement are different in all the 3 examples. So this is an example of, means they are differ in the arrangement of your alkyl groups, which has the same functional group, that is ether, but the alkyl group arrangement is one is ethyl, methyl, and isopropyl. Different groups are attached. So this is an example of metamerism. Tautomerism. This is the most important part. It is very important in your mechanistic approach. So what this is shown, especially by functional group. It's an example, special case of functional group isomerism. In general, tautomers have different functional group and exist in equilibrium with each other. So 2 functional groups, they come in equilibrium with each other. So let us take, and they are interconvertible. They are interconvertible. Let us take an example of acetone, that is in a keto form. There will be a hydrogen transfer. So it gets converted into propene to all. Your acetone gets converted into alcohol and ene. So this conversion, rapid conversion from a ketone to an enol form is known as tautomerism. This rapid conversion from your keto to an enol form is known as tautomerism, and it is referred to as keto-enol tautomerism. Now, the next form of isomerism is your epimers. If you see, this is the change in configuration at a particular carbon atom. So, change in your configuration at a particular stereogenic center. So, let us take an example of glucose, mannose. If you see the structure of glucose and mannose and look at the second carbon. In the second carbon, the glucose, the OH is on the right hand side, whereas in case of your mannose, it is on the left hand side. Rest all structure is same. Such type of isomerism due to the change in configuration at a single stereogenic center is known as epimerism, and the two compounds are isomers are known as epimer. Similarly, if you go to the fourth carbon between glucose and galactose, rest all molecule is same, but at the fourth carbon, the OH in the case of glucose is on the right hand side, whereas in case of galactose, it is on the left hand side, and such is an example of your epimers. So these are epimers. Now let's go for the chirality. So what is chirality or chiral center? As I explained before, it is a carbon with 4 different groups attached to it. It's a carbon center. It's a molecule containing a carbon with 4 different groups. It is also said as asymmetric, stereogenic, or a chiral center. Now let's see the example. Okay, A and B. Let us label a molecule A and B. They are mirror image, but they are not superimposable. If you see A and B, the structure of this compound, chlorine, hydrogen, fluorine, and bromine. If you see that spatial arrangement, it's completely different. They have got a non-superimposable mirror. They cannot align on each other. If you cannot place them one above one. Such type of molecules are said to be chiral, and A and B are different compounds. Okay, they are said to be chiral molecules and they are different compounds. And these are the examples of enantiomers. They don't have similar spatial arrangement. Such type of compounds are known as enantiomer. So how to determine a stereogenic center? How to locate a stereogenic center? So you have to see a molecule. Look out for a carbon which is tetrahedral and which have got 4 different groups bonded to it. You have to locate that. Once you locate that, you have to mark it with asterisk and then you have to give the priority. So if a molecule contains n stereogenic centers, then there will be 2 raised to n stereoisomers. So in the following example, 3-bromohexane. So there the third carbon has 1 hydrogen, bromine, ethyl, and a propyl group attached to it. That's why there are 4 different groups. That's why that particular carbon is said to be stereogenic center or asymmetric center. So let us go into the basics of chirality. What determines chirality? Every compound has a mirror image. So fundamental question, whether the molecule and its mirror are superimposable. Everybody has its mirror image, but whether they are superimposable. If a molecule and its mirror image are not superimposable, so listen carefully. When a molecule and its mirror image are not superimposable, the molecules and its mirror are said to be chiral. So that molecule and its mirror image are said to be chiral. The terms stereogenic center and a chiral are related but distinct. In general, a chiral molecule must have 1 or more stereogenic centers. The presence of plane of symmetry within the molecule makes a compound a chiral. So if there is a plane of symmetry, the compound might be chiral. But if there is a plane of symmetry within the molecule, then such compound is said to be a chiral. Very important. So what is achirality? A molecule that are not chiral if they contain a plane of symmetry, a plane that cuts a molecule in half so that one half is the mirror image of another. So such type of compounds are said to be a chiral. Molecules or objects that possess a plane of symmetry are superimposable on their mirror images and they are said to be a chiral. Now, types of stereoisomers. So, types of stereoisomers. There are 2 types of stereoisomers, enantiomers and diastereomers. So, enantiomers are compounds which form non-superimposable mirror image on each other. Whereas diastereomers, they are the two isomers that are not mirror images of each other. They are not. They are completely different. So geometric isomerism is a form of diastereomers. Cis and trans are the examples of diastereomers. So let's go deep into enantiomers. What are the enantiomers? As explained earlier, they are non-superimposable mirror image of each other. Okay. If you see on the example which are on the right side, there is a mismatch. The OH and H do not overlap. OH and H do not overlap each other. So they are non-superimposable. So when such molecules which are non-superimposable on each other, they are said to be chiral and enantiomers. It is similar to your right hand and left hand. It is similar to your right hand and left. You can see you cannot superimpose your right hand over left hand. You cannot superimpose right hand over left hand. So this is an example of enantiomer. So what are the properties? They have got identical physical and chemical properties like VP, melting point, etc. But they only differ in the ability to rotate the plane of plane polarized. So they differ in the ability to rotate the plane. They rotate the plane of exactly opposite in an equal direction. So if one enantiomer rotates in the right direction, other rotates exactly opposite, that is in a left direction. So enantiomers are said to be chiral. Okay, enantiomers are said to be and they how they react. So these are the way they change. So what is the difference between a chiral and a chiral? What is the difference between chiral and a chiral molecule? Although everything has a mirror image may or may not be superimposable. Okay, a molecule or object that has not superimposed on a mirror image is said to be chiral, whereas examples like socks, they are a pair of images and are superimposed, and the socks and its mirror are identical to each other. So molecule or object that is superimposable on its mirror image is said to be a chiral. So let us see the examples given below. CH2 bromo Br. So when you draw a structure, if you see, it divides into two identical. The hydrogens are there on both the sides. So that side are said to be a chiral because of the plane of symmetry. Similarly, go for another example, a CH bromo Cl fluoro. With all four different groups attached, it is said to be there is no plane of symmetry. Okay, such type of compound are said to be chiral. So this is the difference between chiral and a chiral compound. Now what is stereogenic center and asymmetric center? So as I have said, you have to locate the carbon with four different groups and then assign with an asterisk. So you should not consider, which all things should not be considered. CH2, CH3 group should not be considered as for chiral center. Moreover, any sp or sp2 hybrid, that is triple bond and double bond, should not be considered as an chiral center. So these are the things you have to remember when you are trying to locate your chiral center. So when there are more than two or more, then each and every carbon has to be identified and accordingly you have to decide. So in this particular example, profoxyphene, there are two chiral center. In case of ephedrine also there are two. In case of fructose there are three. You have to identify four different groups which are attached to it and then determine the stereogenic center. This is how. Stereogenic can also occur in a part of a ring. So in a cyclic structure also there can be a stereogenic. How to locate it? How to locate a stereogenic center in a ring? So find the stereogenic center in the carbon. So first of all you have to find a carbon which has got four different groups and it should be a flat molecule in a polygonal. So you have to write it in a flat polygonal way. Look out for the trend and see the different. Now let us see some two examples. Let us take the example of methyl cyclopentane. You got this methyl cyclopentane and look at the carbon 1. It has got CH3H and you got two cyclic ring. But when you try to draw there is a plane of symmetry. You got an upper half and a lower half which are identical to each other. So when such things are occurred in cyclic compound, then the C1 is not said to be stereogenic in nature. Now let's go for the other example, 3-methyl cyclohexane. Let's go for another example, that is 3-methyl cyclohexane. Methyl, hydrogen, and if you see, there is a double bond on the top and there is a saturated portion on the down of the ring. So yeah, so there cannot be a plane of symmetry because all the substitutions attached to the carbon are different. All the substitutions which are attached to the carbon are different. Okay, that's why this particular example of 3-methyl cyclohexane is an chiral compound with a stereogenic center at the C3 carbon. Okay, at the C3 carbon, because there is a difference substitution at the C2 carbons which is present. So that's how they are different. Now let's come to the most important, that is configuration. So what is configuration? It is the arrangement of atoms or group of atoms in the space about the chiral center. You have got a chiral center. How they are arranged across it determines the configuration. It is the arrangement of atoms or group of atoms in the space about the chiral center is known as configuration. So it is the spatial arrangement of the groups of atoms across the chiral center. Okay, there are two types: absolute as well as relative configuration. Absolute configuration is the precise three-dimensional arrangement of the atoms in the space. It is the precise exact arrangement how this thing is arranged in the space across the center. And the relative compares the three-dimensional arrangement of an atom in the space of one compound with those of another. So we are trying to relate the two configuration with the standard. You take, like in case of your carbohydrates, it is related to your glyceraldehyde. So that is a relative standard to which you compare the rest of your series of compounds. So these are the absolute and configuration and relative. These are the two different types of configuration where you can find determine the configuration or spatial arrangement of your chiral or stereoisomers. Now, labeling of stereocenters with R and S. How to label your stereogenic centers with R and S? That is absolute, determining the absolute configuration of your stereogenic center. How to do that? So, since enantiomers are two different compounds, they need to be distinguished by naming. So this can be done by adding prefix R and or S to the IUPAC name of the enantiomers. So you can determine the absolute configuration by giving a letter capital R or S before your IUPAC name. Naming of enantiomers with prefer R and X is called as Kane-Ingold prelock system. It's called as Kane-Ingold prelock system. To designate the enantiomers as R and S, priority must be assigned to each group bonded to the stereogenic center in order of their decreasing atomic number. So first thing, we have to determine the priority according to the atomic number. The highest atomic number is given the first priority, that is the highest priority, and the lowest atomic number is given the lowest priority. So let's see the example with a bromochlorofluoromethane. So it has got a fluorine, bromine, chlorine, and an hydrogen group attached to a stereogenic carbon. Okay, so bromine is atomic number of 79, its first priority. Chlorine of 37 gets second, fluorine of 17 gets third, and your hydrogen with 1 gets your fourth priority. So this is how you determine the priority. This is the first step. Now let's go for the second step. If the atoms of the stereogenic centers are same, so means two atoms attached to the stereogen are the same, then what we should do? Then assign the priority based on the atomic number of the atoms bonded to this carbon. So you have to go for the next atom which is attached to the respective atom, so which is to be seen. So on one atom with an higher atomic number determines the highest priority. So let us take the example that is given over here, that is 2-butanol. If you see, that has got an hydrogen, methyl and an ethyl group and an OH group. First priority as normal, it is OH. Now second, two carbons are attached. Both the groups attached is atoms is carbon. So we have to look out for the next. Since on the right hand side the carbon is attached to 2 hydrogens and 1 carbon, whereas in case of in the left hand side it is 3 hydrogen atoms. So thus we give the priority to the carbon which is on the right hand side because it has got an CH2 and a methyl group, extra methyl group attached. So that's given the second priority, and the third priority goes to your methyl group. This is how you determine when the two groups are having the same atoms attachment. So this is the second group. Now if you have isotopes, if your stereogenic center is attached to an isotope, then assign the priorities in order of decreasing a mass number. Thus, in comparing the three isotopes of your hydrogen, the order of priority is tritium, deuterium and hydrogen. 3, 2, 1 is the mass number and the priority is 1, 2, 3 simultaneously respectively. Now comes the third rule. The third rule says that when your stereogenic center is attached to an multiple bond. So when it is attached to a multiple bond, treat the multiple bonded atom as equal number of singly bonded atoms. For example, your carbon of carbonyl group, that is C double bond O, consider to be the carbon is attached to 2 oxygen. Similarly, the oxygen is attached to your 2. So you are converting the C double bond O to CO, means 2 equivalent single bonds of carbon and oxygen. Okay. So this is how you can draw an equivalent structure. Similarly, can be the example of your cyano. In case of cyano, carbon is attached to nitrogen by a triple bond. So your carbon which is equivalent to 3 single bonds, CN, CN and CN. So 3 single bonds between nitrogen. So this is how you try to simplify or expand the structure and look for the priority. Now if there are common multiple bonds between carbon and carbon, if carbon and carbon double bond, means carbon is attached to 2. If it is triple bond, carbon is attached to equivalent number of 3 carbons. Okay, this is how you kind to determine the priorities, and now you simplify it. Now viewing rule. So how to assign R and S? How to, now you know the priorities, how to give the priorities according to the atomic number. Then if it is a double bond, convert it into equivalent single bonds. This is how we determine the priority. Now how to locate the highest to the lowest. So orient the molecule so that the groups of lowest priority, that is directed away from you. So when you see the molecule over here, you see such that when you see the group of lowest priority, that is 4, it's away from you. That is the first thing that you have to see. Okay. Next thing, orient the molecule so that the group of the lowest, as I said, read the 3 groups projecting towards you in order of your highest to lowest priority. Okay. Read the groups, that is 3 groups projecting towards from highest to lowest. So next thing is you have to read the priorities 1, 2, 3. See the priority of the groups. Okay. Once you have done it, now if the groups you read is in clockwise direction, that eyeball moves in clockwise direction, the configuration is known as R. If the priorities move in clockwise direction, the configuration is said to be R. And if it moves in anti-clockwise or counterclockwise direction, then the configuration is S. Then the configuration is as you can see, the clockwise it is R, and anti-clockwise the configuration is S. So let us take an example of 2-butanol. There are 2 configurations. You can see A and B. You first assign the priorities, decreasing priority. OH first, methyl, ethyl second, methyl third, and H is the fourth. So once you determine the priority, this is labeled. So what is the next step in this? Now keep your hydrogen which has the lowest priority at the back. Now look at the three groups other than that. Your OH, methyl and ethyl group. How they are? So in case of enantiomer A, your OH, then it is followed by ethyl and methyl. So it is in one direction. B, OH, methyl and ethyl is in the exactly opposite. So 1, 2, 3. In case of A, that is in clockwise direction. 1, 2, 3 is in anti-clockwise direction in case of your enantiomer B. So now you know which is clockwise and which is anti-clockwise. So next step, if it is an clockwise direction, the enantiomer A is supposed to be an R isomer, and if it is an anti-clockwise direction, then it is, or the counterclockwise direction, then the isomer is supposed to be of S configuration. So in this case, your B example is an enantiomer is of S configuration, whereas your A enantiomer of butanol to butanol is of R. And you write it R bracket, capital R bracket 2. That is your name of your compound. So this is how you represent a stereogenic absolute configuration of a compound. Now these are some of the examples of how to determine the priority. In this particular example, if you see bromo, chloro, iodo, though it is attached to the carbon, but it is not directly attached to the stereogen. That's why it is given the third priority. This is how you try, because iodo is not directly attached to your stereogenic center. Next case, if you see, the highest priority is given to your isopropyl group because it has got 2 carbons attached, followed by your 1, 2, 3, 4, 5. So if you see, it has got an pentyl group, whereas the third has got an propyl group, and the fourth one is just your methyl group. This is how you give the priority when the carbons are same. So this is how you try to find. The next one example is, in this case, OH is given the first priority because oxygen has got an highest atomic number, followed by your carbonyl group because your carbonyl group COOH. So COOH means your carbon is attached to your 2 oxygens. So that's why it is given the second priority, whereas in case of your next CH2OH, because it is attached to your only carbon and 2 hydrogens and oxygen. So this is how you try to give the priority and assign the priorities to your stereogenic centers. So this was about absolute. Now we will go towards your relative configuration, that is Fisher's DL nomenclatures. That is Fisher's DL nomenclature. This is to find the relative configuration of your stereoisomers. Okay. In this system of assigning relative configuration to a molecule by establishing configurational relation among the members of a family of compounds. Like family of compounds means like examples carbohydrates and amino. So one group of compounds, their carbohydrates are simple one family of compounds. So you have a reference standard for that. You have a reference standard. So glyceraldehyde is chosen arbitrarily as a standard. Glyceraldehyde is arbitrarily chosen as a standard. So let us see the structure of glyceraldehyde. So you have got an aldehyde followed by HOH and another alcohol, CH2OH. Your stereogenic center contains your is connected to an aldehyde, OH, H, and your methanolic alcohol. So these are the 4 groups that are attached to your stereogenic center. Now let us see, when the OH group which is present on the stereogenic center is on the right hand side, if you see, then it is called as D. It is said to be of a D configuration, and when the OH group is on the left hand side in your Fisher formula, then it is said to be of your L configuration. This is how you try to determine where glyceraldehyde acts as a standard benchmark. Now let us go how to determine the rules of assigning the DL nomenclature to your carbohydrates. So let us take an example of your L-triose and D-triose. So if you go through the example, if you see first, what you have to take? You have to say the longest carbon chain should be placed vertically in the Fisher form. So in this case 1, 2, 3, 4 carbon. That is the longest chain of your carbon. That has to be aligned in a vertical line. Next thing is most oxidized end of the carbon is placed at the top. So in this case, if you see, there is an aldehydic group and there is an alcoholic group. The most oxidized state is your aldehydic group. So that will always be on the top. So aldehyde will be in the top. In case of ketones like fructose, the ketone group will be considered as the topmost group. Okay. So once this is finalized, then you have to next, if you have to see for the group which is at the bottom of the line, bottom of the chain, which is the group OH and the stereogenic center containing OH on the last stereogenic center. We have to go to the last stereogenic center. Then look out for the OH group. So let's, in case of L-threonine, if you see the last group, last stereogenic center contains the OH group on the left hand side. That's why it is called as L-threose. And in case of D-threose, the last OH group in the stereogenic center containing the stereo, it is on the right hand side. So this is how you determine the D and L, and it is capital D and capital L. So, and the reference standard is glyceraldehyde. As you have seen earlier, it is the glyceraldehyde that has to be considered as your example. Similarly, in case of glucose, if is when the D-glucose contains your OH, that is the last stereogenic center contains the OH at the right hand side, that is D-glucose, and the one which is on the left hand side is known as L-glucose. This is how you give the nomenclature for your relative configuration. And we know that if there are n number of stereogenic center, then the total number of stereoisomers that can be formed is 2 raised to n. That if it is n is equal to 1, there are 2 stereoisomers can be formed. If n is equal to 2, then there will be 4 stereoisomers that can be formed. Okay. Now there is one more nomenclature, that is erythrose and threose. So erythrose means when the two groups, if you see in over here, OH containing or NH, are on the same side. If the two similar groups are on the same side, like OH, NH, like H and H, let us consider H and H. So if H and H are on the same side, then it is have to be an erythroform. And when the two substituents are on the opposite side, okay, of the Fischer formula, then it is said to be of trio configuration. This is also a method of determining the configuration of your compounds. Next comes diastereomers. So as explained earlier, what are diastereomers? They are example of geometric isomers. Okay, they are the stereoisomers whose molecules are not mirror images of each other. Enantiomers are non-superimposable mirror image, whereas in case of diastereomers, they are not mirror images of it. They are completely different configuration. Their mirror enantiomers differs in configuration at 1, whereas in this thing they do not superimposable at all. You take the example of 1, 2, 3 dibromopentane. Okay, if you see the particular example, you got 2 stereogenic centers. Okay, and now see, these are the, and when you draw its mirror image, they are okay. These are enantiomers. Now let's go for the next thing. So there will be 4 enantiomer stereoisomers. So these are the 4 different configurations. So if you see A and B, they are mirror images of each other, where the CH2 and CH3 are on the do not superimpose, and even C and D, it is the same. But when you compare A with C and B with D, they have got an entirely different configuration. Special array. They do not superimposable and they are not mirror images of each other. Such type of compounds are called as diastereomers. Such type of compounds are called as diastereomers. Example of cyclic compounds also you can take your cis and trans. In cis, 2 methyls are on the same side, whereas above the plane, whereas in trans there are 1 So these 2 compounds are said to be diastereomers because they do not form a superimposable mirror images. Okay, they are not mirror images. Similarly, in case of cis and trans, double bond. Cis, the two similar groups are on the same side, whereas in trans they are in opposite, so they do not form mirror images, so they are said to be diastereomers. Now let's go for the difference between enantiomers and diastereomers. Let's go for the difference. So what are enantiomers? As said earlier, they are non-superimposable mirror images, whereas diastereomers, they do not form a non-superimposable mirror image. So that's the first thing on the mirror images tab. Second is the physical properties are identical, whereas in case of diastereomers, they have different physical properties. They have identical chemical properties in enantiomers, whereas diastereomers might have similar but not identical chemical properties. Okay, they rotate the plane of plane polarized in equal but in opposite direction. But these diastereomers, they may or may not rotate the plane of plane polarized light in the same direction but to a different direction. So it might change, but it will be to a different extent. They cannot be separated from each other by any physical methods. Yeah, you cannot separate enantiomers, but the diastereomers can be separated by physical methods like fractional crystallization, distillation, etc. They are optically active. Diastereomers may or may not be optically active. The examples, you can give the following examples. You can see the chloro in case of enantiomers have got different configuration. Whereas in the case of diastereomers, they are non-mirror image. Whereas in case of enantiomers, they just form non-superimposable mirror. So this is the difference between your enantiomer and diastereomers. Now let's come to the next compounds, that is mesocompounds. What are these mesocompounds? So as you can see, mesocompounds contain chiral atoms. They are chiral atoms, but still they are occurring because they contain a plane of symmetry, because they possess a plane of symmetry. If you can see in the particular example of tartaric acid, you can see COH, H and OH on both the chiral centers, and if you cross section it, they are exact mirror images of each other. So they are exact. So your bottom half is the mirror image of your top portion. So the mesocompounds generally contain a plane of, and they possess identical halves. And the mesocompounds are the compounds with chiral but are. This is the reason why they are optically inactive. So this is another example of your mesocompounds, 2,3-dibromobutane. If you can see this structure, A and B in this form, if you see, they are mirror image. If you can see, the bromo positions are different. Okay, that is enantiomers. But C, when you see the C compound, methyl bromohydrogens in both the compounds have got same arrangement, spatial arrangement. So, and they got a plane of symmetry between them. That's the reason why they form two identical halves, and they are optically inactive, and they are said to be mesocompounds. They are said to be mesocompounds. Okay, this is the examples of your mesocompounds. A and B are meso, and C is said to be, A and B are enantiomers. C is said to be an mesocompound. A and B are diastereomers of C because they do not form mirror images of each other. So A and C and B and C are said to be diastereomers. Now the most important thing. So when you are assigning two stereogenic, you have to know the configuration of both the carbons. If there are more than two stereogenic centers, you should know the absolute configuration of both the carbons. And this is very much important to determine the configuration, whether the compound is identical, enantiomer, or an diastereomer. This can be. So let us say, first thing. So identical compounds. Let us say the identical compounds have the same R and S designation at every tetrahedral stereogenic center. Means they'll have the same configuration. Even if you try to flip it, do anything, they will have an identical conformation. If the configuration is R and S, the product's configuration, the next stereomer's configuration is so will also be R and S. Now let's go for enantiomers. So in enantiomers, they should have exactly opposite. So the two stereogenic centers, if they have, let us take an example, then let they have two stereogenic centers. One has R at one center and other has S at one center. Now when you flip it, go to another stereoisomer of that enantiomer, it will, the first one will be S and the other one will be R. So both the configuration changes in case of your enantiomers. Now let's go for the diastereomers. In diastereomers, what does it say? That one of the configuration remains constant and other changes. So they form non-superimposable, non-mirror images of each other. So this can be explained by your tartaric acid. So if you see tartaric acid, okay, the enantiomeric RR, it's this thing will be, enantiomer will be SS. So exactly opposite. If you see, so that satisfies. Diastereomer, you got another group, that is when OH groups are anti to each other. So one configuration when OH groups are syn. At syn means at the same position. The other configuration when the OH groups are on the opposite side. So you get an RS and SR configuration. But if you see written over there, the compounds on the right hand side are said to be achiral. They are not enantiomers. Though they have got different configuration, arrangement, but still they are said to be a non-enantiomers. Why? Because they are mesopair. They have got identical configuration. If you try to flip, you get the same molecule. If you try to flip and they superimpose on it. So these are the examples of your identical meso compound. And from this particular picture, we can see that the groups are on the left hand side are enantiomers and they form a diastereomer combination with the groups on the right hand side when the OH groups are on the anti configuration. So this is how you can differentiate between your enantiomers, diastereomer and meso compounds, and meso compounds are basically identical in nature. Meso compounds are basically identical. Why? You can see this thing over. If you try to rotate by 180 degrees the molecule, you get the exactly the same configuration. So that's why RS and SR are the stereoisomers are identical because the configuration remains the same. The RS and SS stereoisomers are superimposable on their mirror images. They are the same molecule and it is not correct to describe them as separate species or a separate because they remain the same. That's why they are said to be identical in it. And the meso compounds, though it contains asymmetry, but their mirror images are superimposable on each other. Mirror images are superimposable on each